Standard silicon solar cells are now asymptotically approaching their absolute physical limit for converting sunlight into usable electricity. Theoretical single-junction silicon efficiency is capped at roughly 33.7%, a ceiling defined by the Shockley-Queisser limit. Reaching a fraction of that limit requires a manufacturing process relying on immense heat and continuous vacuum environments to produce brittle blue silicon wafers. This bar chart breaks down the solar supply chain stages. Data from the International Energy Agency shows that this highly energy-intensive process is concentrated in a single region, which currently manufactures 95% of the world's photovoltaic wafers. Supply chain analysts model this as an N1 failure risk. Under this scenario, the loss of this single major exporter would result in the immediate halt of global solar deployment. The material constraints limiting silicon's efficiency are the exact same constraints mandating its centralized, capital-intensive manufacturing. The primary challenger to this status quo is the hybrid organic-inorganic perovskite solar cell. Unlike silicon ingots, fabricating perovskite does not require extreme heat or high vacuum environments. Instead, the materials are applied through solution processing. By utilizing low-temperature wet chemistry, liquid perovskite ink is directly deposited onto a flexible substrate. Since their initial use in 2009 at 3.8% efficiency, laboratory-scale perovskite devices have rapidly scaled to 27%, matching the performance of standard silicon. By shifting the material base from a rigid ingot to a printable ink, the industry gains a new set of options for where and how solar cells are made. To understand how printed liquid rivals refined crystal, we must look at the sub-nanometer scale. This is a 3D model of the perovskite ABX3 crystal lattice. It consists of an organic or inorganic cation, labeled A, a metal cation, labeled B, and a halogen anion, labeled X. This structure possesses a uniquely low exciton binding energy. When the lattice absorbs a photon, it spontaneously generates an electron-hole pair that easily separates at room temperature and travels through the material. Silicon requires near-perfect crystalline purity to function. Perovskite exhibits defect tolerance, operating highly efficiently even when deposited as imperfect polycrystalline thin films. The lattice also allows for precise bandgap tunability. By swapping specific halogens in the X position, such as mixing iodine and bromine, engineers can alter the specific wavelengths of light the crystal will absorb. This chemical tunability means perovskite can be precisely customized to capture the exact spectrum of sunlight that silicon misses. Standard single-junction cells lose high-energy photons to thermalization, dissipating them as heat. Multi-junction or tandem solar cells prevent this loss by stacking different bandgaps. This is an isometric cross-section of a two-terminal perovskite-silicon tandem cell. A thin perovskite top layer is separated from a thicker silicon bottom layer by an interconnection layer. The perovskite top layer is tuned to a wide bandgap between 1.6 and 1.8 electron volts, positioning it directly above the 1.12 electron volt silicon subcell. High-frequency blue and green light is absorbed entirely by the perovskite. The remaining low-energy red and infrared photons pass cleanly through the top layer, stopping inside the silicon layer below. The strict engineering constraint of the two-terminal architecture is that the subcells are wired in series. This requires precise electrical current matching between the top and bottom layers to prevent current loss. By satisfying this constraint, the theoretical efficiency limit of the tandem cell jumps to 45.3%. Certified laboratory devices have already achieved 34.85%. By mechanically stacking these tuned bandgaps, engineers have bypassed the theoretical ceiling of a standalone silicon cell. Translating laboratory efficiency to commercial reality requires returning to the factory floor. Traditional silicon infrastructure demands immense capital expenditure for heavy robotics and massive facility footprints. This levelized cost breakdown chart highlights the economic burden. International Energy Agency data shows that over 2/3 of the manufacturing cost gap between regions is driven by structural energy and labor inputs. Perovskite solution processing bypasses these structural costs entirely. Manufacturers can deposit the active layers using straightforward solvent techniques, like spin coating or blade coating. Stripping away the extreme heat and vacuum stages reduces localized energy demands to a fraction of what standard photovoltaic manufacturing requires. The physics of wet chemistry alter the capital requirements for solar production, lowering the barrier to entry for regional manufacturers. Lowering capital expenditure shifts the global economic map. This map illustrates the flow of clean energy components. True supply chain security requires mitigating the risks at critical trade choke points, like the severe bottleneck radiating from East Asia through the Strait of Malacca. The International Energy Agency models a strategic alternative, separating component manufacturing based on regional strengths. Under this model, importing raw wafers from North Africa to be finished into modules within the European Union cuts production costs by nearly 20% compared to a fully domestic European module. Because perovskite final stage printing requires low capital expenditure, this decentralized manufacturing becomes economically viable far outside of Asia. This regional manufacturing model relies on the low capex nature of perovskite to function, providing an alternative to the geographic concentration of traditional silicon. Despite the low costs and laboratory records, perovskite solar cells remain largely absent from the commercial market. The primary physical vulnerability is the organic component of the lattice. Because it is highly water-soluble, the material degrades rapidly upon contact with moisture. The lattice is also soft. Under applied heat or electric bias, halide ions migrate through the structure. This creates internal electric fields that disrupt the cell's operation and kill efficiency. This internal ion movement produces a measurement ambiguity known as J-V curve hysteresis. This graph demonstrates the effect. Scanning from forward bias to short circuit produces a completely different curve than scanning from short circuit to forward bias. This wide hysteresis loop inflates reported laboratory efficiencies. To find the true stabilized power output, researchers must hold the device at strict maximum power point tracking over time. Because of these unique degradation mechanisms, the standard testing protocols designed for silicon wafers are insufficient for measuring the lifespan of perovskite cells. Commercialization relies entirely on the engineering ability to lock this soft, ionic lattice into a stable and enduring state. The final barrier to widespread adoption is the environmental hazard posed by the lead contained within the ABX3 structure. Hybrid perovskites easily degrade into highly bioavailable lead compounds. If a solar module is cracked by severe weather, this toxic heavy metal risks leaking into the environment. To mitigate this, engineers are integrating self-healing epoxy resins and cation exchange resins directly into the module. Through diffusion-controlled processes, these coatings chemically bind and permanently sequester escaping lead. Advancements have been made in end-of-life recycling. New aqueous green solvent systems chemically coordinate with acetate ions, safely extracting over 99% of lead iodide. Transitioning the physics of light absorption from rigid, energy-intensive silicon ingots to tunable, low-temperature liquid inks changes the industrial requirements for solar power. 3 distinct engineering hurdles remain: stabilizing internal ion migration, standardizing true maximum power point tracking, and safely mitigating lead toxicity. Solving this trilemma is an economic and geopolitical imperative, because whoever masters the perovskite lattice holds the ability to reorganize the global solar supply chain.